Students, in this class, we will study about the nth root of a complex number. Now, foremost, you need to know what do you mean exactly by this term nth root. Now, suppose you are having a quantity like x raised to the power 5 is equal to 1. And I want to find x. So actually, if you are going to be raising both sides to the fifth root, then you would be having x to be equal to the fifth root of 1. And we write it like this. Okay. Now, in this case, in general, we are talking about the nth root of a complex number. So I have taken the right side to be 1. Now, it need not have to be 1. In this case, it is the fifth root of unity. Now, to explain it for any quantity, we would be taking a complex number z to be of the form x positive iy, and then we would proceed. Now, just to give you some refreshment from algebra, if you are given a quantity, say x squared is equal to 25, and they are asking you to find the value of x, then you are exactly taking the second root of 25. We call it a square root. Now, that is going to be equal to plus or minus 5. So I'm taking here a positive 5 here. Now, if you are given, say, x to the power 3 is equal to 8, and they are asking you to find x, then what are you doing here? You're taking the third root of the number 8. So that can also be written as 8 raised to the power 1 over 3, and which would be again rewritten as 2 raised to the power 3 raised to the power 1 over 3, which would be giving us x is equal to 2. So this is the third root of the number 8. This is the second root of the number 25. So like that, we are asked to find, in general, any root for a given complex number. So that's the reason I'm specifying it as nth root of a complex number. Now, there are two parts in this particular topic. So one is to find the nth root of a complex number. The other one would be to find the nth root of unity. Okay, I just explained to you, if I were to have the number 1 on the right side, and we are expected to find the value of x, then I would say this quantity on the right side to be as the fifth root of unity. So in that same manner, we are expected to find the nth root of unity. So that would be my second part. So my first part for this explanation would be how to find the nth root of a complex number. So having said that, let me proceed to the given topic. Now, let me take any complex number z of the form x positive iy. Now, if I were to find r, which is the modulus, then the quantity is going to be x squared positive y squared. Now, I need to find alpha. Now, alpha is going to be tan inverse of y divided by x. Of course, you need to place it in the modulus sign. Now, this is not theta. Okay, now this is just the reference angle. Now, to find theta, I have told you the following information about the quadrants. So we got 4 quadrants. Now, if the complex number z were to be present in the first quadrant, then I would have the actual theta to be alpha. Now, if it were to be present in the second quadrant, then the theta would be pi negative alpha. The third quadrant, theta would be pi positive alpha. The fourth quadrant, theta will be negative alpha. So this is just your reminder, just to make you understand that we have already done this, but just to form as a review. Okay, now having obtained this complex number z, which is x positive iy, can be written in polar form as r of cos theta positive I times sine theta. Now, this can also be written using the representation r cis of theta. Okay, cis means cos theta positive I sine theta. So that is just as a representation. You don't need to be writing it as shown here in complete elaboration, but it is your choice. So this complex number x positive iy is represented in this manner. Now, if we were to represent the quantity in Eulers form, then we would be writing the complex number as z is equal to r times e raised to the power I theta. So this is the representation given by Eulers. Okay, so using this representation, we can actually obtain the nth root of any complex number for that matter. Now, if we were to extend this for any coterminal angles, then z would be r of, in other words, r times e raised to the power I of theta positive 2 pi k, where k is element of integer. Now, I'm going to show you what happens when k is equal to 0. Now, when k is equal to 0, we would get z to be equal to r times e I of theta positive 2 pi of 0. So, what would this be? This quantity is going to be giving us r e raised to the power I theta. So this is what we are getting. Now, before we could proceed here, now suppose, let us assume that if we are expected to find z raised to the power 1 over n, in that case, this right side is going to be r times ei of theta positive 2 pi k raised to the power of 1 over n. Okay. Now, this can be further rewritten as r raised to the power 1 over n e raised to the power I times of theta positive 2 pi k. Using the law of exponents, this can be written like this. So this is going to be z raised to the power 1 over n. Now, if I were to take k is equal to 0 for this quantity, then I'm much bothered about the exponent of this region. So I would be getting theta for k is equal to 0. This is going to be vanishing, right? If this vanishes, I would just left with theta divided by n. Okay, for k is equal to 0. Now, when k is equal to 1, this is going to be theta divided by n positive 2 pi, k is 1, divided by n. So this is going to be the quantity, right? So when k is equal to 2, this is going to be theta divided by n positive 2 pi of 2 divided by n, and so on. For k is equal to n minus 1, this would be giving me theta over n positive 2 pi of n minus 1 divided by n. Now, when k is equal to n, you would get theta over n positive 2 pi of n divided by n. So that would be giving you theta over n positive 2 pi. So that means you would be repeating, okay, you would be repeating the values from theta is equal to 0 again. So the values would become redundant. So if I were to take z, the nth root, okay, the nth root of the complex number, then the formula becomes z raised to the power 1 over n is equal to r raised to the power 1 over n e raised to the power I of theta positive 2 pi k divided by n, where k is element of integers and the values of k will be 0, 1, 2, etc. up to n minus 1. So this is going to be the required formula for finding the nth root of any complex number. Find the cube root of this complex number, z is equal to negative 3 times root of 2 divided by 2 positive I times 3 times root of 2 divided by 2. So this is the complex number. So let us write that down. Now, after writing it down, we need the formula to solve this question. Now we have already got this formula. Z raised to the power 1 over n is r raised to the power 1 over n times e raised to the power I of theta positive 2 pi k divided by n. K is element of integers and k stretches from 0 to n minus 1. Now I can rewrite the formula to be as z raised to the power 1 over n is equal to r raised to the power 1 over n cis. Okay, this is a very important representation that comes in handy. So cis of theta positive 2 pi k divided by n. Okay, where k is equal to 0, 1, 2, up to n minus 1. So remember this representation. It is very useful and we can do this question using this representation. Okay, so now foremost we have to obtain r. So from the given complex number I'm going to take 3 out and write this as 3 of negative root of 2 over 2 positive I times root of 2 over 2, which is z raised to the power 1 over n is equal to r raised to the power 1 over n cis of theta positive 2 pi k divided by n. Of course, k stretches from 0, 1 to n minus 1. Now we are asked to find the cube root. Now when we asked to find the cube root, the value of n is going to be equal to 3. So have that in mind. The value of r is found to be as 3. For the problem, okay, the given problem is z is equal to negative 3 times root 2 divided by 2 positive I times 3 times root 2 divided by 2. Now the question comes, what is the value of theta? Now before we could proceed to the value of theta, we have to find the value of alpha, right? So that is critical. So alpha is equal to tan inverse of y divided by x. No, because if z is equal to x positive iy, then alpha would be tan inverse of y divided by x, of course with the modulus sign. So in this case it is going to be, now we have to place this is going to be my x, this is going to be my y. So if I were to find the tan inverse, so that's going to be tan inverse of 3 times root 2 divided by 2 divided by negative 3 times root 2 divided by 2. Of course we need to place the modulus sign, so that's going to be tan inverse of 3 times root 2 divided by 2. When you flip it, it's going to be 2 over 3 times root 2. Of course we have a negative sign, but that's not going to be affecting us because we got the modulus sign here. So what happens here, we are having a complete cancellation of the quantities resulting in tan inverse of 1. Now the question is, what is tan inverse of 1? We know that tan inverse of 1 is pi divided by 4, but we need to get theta. This is just the reference angle. Now the complex number is of the form negative. So z is actually negative 3 times root 2 divided by 2 positive I times 3 times root 2 divided by 2. So if we were to locate this complex number, then negative x will be on the side, but y is actually positive, so this will be landing up in the second quadrant. Now I have already mentioned to you, if it is in the first quadrant, theta will be alpha. If it is in the second quadrant, theta is going to be pi minus alpha. So to get theta, we need to have pi minus the quantity pi over 4. That would be giving us theta to be as 3 pi over 4. So we have got theta. Now all it matters is we need to write the final answer. So using, I can write that, using z raised to the power 1 over n is equal to r raised to the power 1 over n cis of theta positive 2 pi k divided by n, we get, of course, the value of k is going to be, we are expected to find the third root. So k is going to be 0, 1 and 2. And we know the value of r is equal to 3. The value of n, we also know n is equal to 3. And we need to actually take the value of k to be as 0, 1, 2, and 3, and so on. So using these values, we would be obtaining the third root. So z raised to the power 1 over 3 is equal to, my quantity for r is 3 raised to the power 1 over n, that's going to be 3 there, and cis of the value is going to be theta positive. For k is equal to 0, for k is equal to 0, this is going to be 2 pi of 0 divided by 3. And we know the value of theta. Theta is going to be 3 pi over 4. And we would have to use this value. Now, so this, upon rewriting, this would give me 3 raised to the power 1 over 3 cis of, this is going to be 0. So we've got theta divided by 3. And using theta to be as 3 pi over 4, I can rewrite this as 3 raised to the power 1 over 3 cis of, this is 3 pi over 4. Okay, you got a 3 there. And that would be giving us 3 raised to the power 1 over 3 cis of pi over 4. So this is the first value for z raised to the power 1 over 3, the first value. This is the value that we are getting when k is equal to 0. Now when k is equal to 1, so I have got all these things taking k to be equal to 0. Now when k is equal to 1, what will be the value? So k is equal to 1, this is going to be z raised to the power 1 over 3 is equal to 3 raised to the power 1 over 3 of theta positive, k is equal to 1, so place the 1 divided by 3, which is 3 raised to the power 1 over 3 of cis, actually I should place cis there, cis of theta positive 2 pi divided by 3. Now this can be rewritten as 3 raised to the power 1 over 3 of cis. Now I can substitute the value of theta, which is 3 pi over 4, 3 pi over 4 positive 2 pi divided by 3. Now this is equal to 3 raised to the power 1 over 3 cis of, this 4 times 2 is 8. 8 added with 3 pi would give me 11 pi. Okay, 11 pi divided by 4. There is a 3 there, so you need to place that 3 also. So this can be rewritten as 3 raised to the power 1 over 3 cis of 11 pi divided by 12. So this is the value that I'm getting. This is the second root. This is the first root, second root, and we've got one more to go. That would be the third root. So we would be again using the formula z raised to the power 1 over n is equal to r raised to the power 1 over n cis of theta positive 2 pi k divided by n. Okay, we are using the same formula. So using the same formula, now z raised to the power 1 over 3 is equal to 3 raised to the power 1 over 3 cis of theta. For this, k is equal to 2. Positive 2 pi of 2 divided by n. The value of n is 3. And that is going to give us 3 raised to the power 1 over 3 cis of theta positive 4 pi divided by 3. Now we are substituting theta is equal to 3 pi divided by 4. So that is going to be giving us 3 raised to the power 1 over 3 cis of 3 pi over 4 positive 4 pi divided by 3, which is equal to 3 raised to the power 1 over 3 cis of 16 plus 3 will give you 19 pi divided by 4. We need to multiply by 3, and that's going to be 3 raised to the power 1 over 3 cis of 19 pi divided by 12. This is z raised to the power 1 over 3. Okay, so I have got all the three roots. Okay, for k is equal to 0, I have produced the root k is equal to 1 and k is equal to 2. So finally we can just sum up the roots that we've got. So therefore the roots are, for k is equal to 0, I'm getting 3 raised to the power 1 over 3 cis of pi over 4. K is equal to 1, 3 raised to the power 1 over 3 cis of 11 pi over 12. And k is equal to 2, 3 raised to the power 1 over 3 cis of 19 pi divided by 12. So these are the three roots. In other words, they asked us to find the third root of the complex number. So we have obtained all of the roots that the question wants us to find. So